My problem A is about a chicken nugget, which is a sphere, and it covers the conduction equation. You have to derive that equation and then find the temperature at a certain radius. So this problem, you can assume that it's 1D, steady state, there's no heat generation, constant K, and the chicken is water, and you'll get these properties. And then it covers topic 2A, derive with the boundary conditions, and I started from the energy balance this time. Did my derivations with the boundary conditions. I solved for the C's here, and I got that equation, and I plugged in 0.01 meters because that was the radius that I chose, and I got that temperature, which covers 2B, which is solving this equation. Problem B is a resistance network through a cylinder, and there are some weird materials used. You're going to assume that it's 1D in the radial direction, steady state, and constant thermal properties. You will find those properties, and it covers 5B cylindrical because I did do it in a cylinder. And then it covers the resistant network. Here you can see that I'm finding those resistances, and then I total them up for our total right there. And that's the answer I came up with. This problem is about a black asphalt pipe, and you're going to look for the heat loss due to natural convection and radiation. So you are going to assume that steady state, the pressure is at 1 atmosphere and the air is at ideal gas. You get more properties for this one, and then you start by finding the Rayleigh number, which that covers natural convection, 7C, Nusselt number, heat transfer coefficient, and then that's the heat loss due to the natural convection. And then you will do the radiation portion, and that covers 1C radiation. Total those up, and that is what you get for your answer. Problem D is about heating whole milk to make hot chocolate. It is a heat exchanger, and then you're going to take that pipe that was in the heat exchanger and modify it so it's a heating element, and you can look for the critical heat flux. So you're going to assume that it's steady state, it's a smooth tube, and there's no heat loss to the surroundings. These are the properties for the first part of the problem. You find the heat transferred. This whole problem is about a heat exchanger, so that covers 8A. You find the velocity, then the Reynolds number. It was turbulent, so you can use this equation for the heat transfer coefficient, which is internal forced convection, which covers 7A. And then you get the overall heat transfer coefficient. And then you find the total heat transfer, and you'll need this log mean temperature difference. And then for the second part, which you're finding Qmax, there's more properties that you'll need. You find this L, which is a dimensionless quantity, and then C crit. Then you use a table to find out what that value is. And then you'll plug it into this Qmax equation, which covers 7D boiling, and get that as your answer. Problem E is a membrane problem, and you're going to find the permeance of hydrogen, and your guess was that this membrane was made of ZIF-8, and you have to decide if it actually was made of ZIF-8. So here's my drawing to show that it is a membrane system, which is AB. Going to assume negligible boundary layer resistance. The membrane is perfectly selective for H2, and there is no sweep through the membrane. This is the permeance that I found for ZIF-8 online, and you will find those mole flows and then your partial pressure, and then you'll put into this change in P, and then you'll use like the flux equation with permeance and the pressure drop to find out what that permeance is, which I got that, and I decided that it wasn't ZIF-8 because this number is pretty different from that one. Even if it wasn't perfectly selective, it should still be closer, so not ZIF8. And this covers the steady state mass transfer as well, which is 6A. Finally, problem F is about hydrogen gas going into a wall. You are going to assume that it's 1D, there's a constant CAS, no reactions, and constant diffusivity. You'll find that diffusivity for hydrogen and nickel, which is what I chose for the wall. And then you'll do this transient mass transfer. You'll have to look up this error function and then do some rearranging, and you'll find that the time is really high, but that is because that I chose 2 centimeters deep into the wall, so it's going to take a really long time for it to go that far. If it had been a shorter distance, it wouldn't have taken as long.